Hello everyone, this is Dr. Hopkins recording the next video in our series of videos for 472. And this one's about thermochemistry. Primarily, this is a general chemistry review. All right, so our review of general chemistry. So right now we're going to talk about enthalpy. Just to remind you what you did in terms of general chemistry. Although before we start on that, I do want to say we're kind of a little out of place. So far in our discussion of thermodynamics, we've talked about first law in closed systems and isolated systems where we have no mass flow. When we talk about chemical reactions, we are definitely having mass flow from reactants to products. Okay, so it's a little out of place, but we've done it before, so we're just going to kind of review at this point. So basically any process, as we've discussed, physical or chemical, so melting, boiling, etc., they have an enthalpy change, right? So there's an enthalpy change associated with that particular process. And as we know, enthalpy was developed for pressure and temperature are the natural variables, right? So if we think back to how we write the differential for dH, it's always in terms of dP and dt. So if we're looking at a particular reaction enthalpy, so a chemical process enthalpy change, the delta H at a standard, we typically want to define, so delta H, a change in enthalpy, is with respect to, you start at one state and you end at another state. Well, the nice thing is we want to define a standard state when we think about a reaction, because you can run a reaction at any particular temperature and there will be changes, or any particular pressure and there'll be changes to that. So it's nice to have kind of a standard set of, okay, we're going to set this as our bar, and then any changes from that we'll worry about. Okay, so in a standard state, you defined it in Gen Chem, is typically 298 Kelvin and 1 bar, or basically 1 atmosphere pressure. Sometimes the temperature is 273 Kelvin for standard, but I think it's pretty much accepted that 298 is a better one. We use this little, I don't have the symbol in PowerPoint, but there's a symbol for the standard state symbol above the delta H that shows that it's defined at those particular pressure and temperature. And so our reaction enthalpy we can use, remember you could determine it by calorimetry, which we're not going to talk about here, or you can determine it using other sets of reactions. So if you have reactions with known enthalpies, that's the idea of Hess's law. This is a really simple concept because we know that enthalpy is a state function, so as long as we know the initial state and the final state, it doesn't really matter how we get there. So as long as we can define the reactants, define the products, and find reactions with enthalpies along the way, we can determine the reaction enthalpy of an unknown reaction. And so here we have also what are common to use are a set of formation reactions. Formation reaction is the creation of the molecule from its elements. So if you have an oxygen in it, you're using O2. If you have carbon in it, use carbon graphite, and so forth. And so there's a series of reactions. They're not particularly important other than that they are quantified. There are lots and lots of them quantified. So you have tables and tables of these reaction enthalpies for formation reactions. And so if you can do the sum of the products minus the sum of the enthalpies of the reactants, and that will give you your reaction enthalpy overall for a particular reaction. And you learned how to do that in general chemistry. And all of this works because, which you didn't learn in general chemistry, is because enthalpy is a state function. And so it doesn't really matter. We don't care the path. As long as we start here and in there, we'll get the right answer. All right. So this is the new part we're going to introduce to our thermochemistry, which is temperature dependent. So that was all under standard conditions. We could determine the enthalpy of a reaction under standard conditions. Now we could measure it in calorimetry, but let's see how we could use this idea of being a state function and some of the thermodynamics we've learned to adapt. So as we know, at constant pressure, like atmospheric pressure, the enthalpy is Cp dt, right? So we have a heat capacity that determines how the enthalpy changes with temperature. So if we have a reaction, let's say A to B, so A are reactants and B, if we run it at 298 Kelvin, the delta H of that reaction would be determined based on the last page. We'd have a formation reaction for A, formation reaction for B, and we'd figure this out. But let's say we're not doing it at 298 Kelvin. We could do it at a lower temperature. We could do it at a higher temperature. It doesn't really matter. So the way we would evaluate that, so we can change this, right? This is a state function. So why don't we take A, pure substance, like we've been dealing with in first law. Let's heat it up to T prime and look at the enthalpy change. And that would just be this integral of Cp dt. So that's if Cp is constant. We'll do the same thing for B. We'll heat it up to T prime, and we'll figure out what's the enthalpy change by heating those two components up, both the reactants and the products up. And if we add those two together to the initial at 298, we get our overall enthalpy of reaction at that particular temperature. And so this idea of using these heat capacities, and actually we can simplify this into Kirchhoff's law. There's a delta reaction Cp, which is just the Cp of the products minus the sum of the Cp's of the reactants, kind of like shown here, assuming that Cp is constant. Now, if we had our heat capacity dependent on temperature, so as a function of T, this wouldn't be a simple integral where you pull this out, do dt. We'd actually have to integrate this with respect to temperature and figure it out and so forth. And that sometimes happens. We might actually have to worry about how the heat capacity changes as the temperature changes, because it really is going to do that. And so until next time.